Good morning, students. In the last class, we discussed about the three different colligative properties of the solutions. In that, what we discussed in the last class, relative lowering of vapor pressure, elevation in boiling point, depression in freezing. So, in today's class, I am going to tell you about another important colligative property, that is osmotic pressure. So what is this osmotic pressure? So listen, I'll explain one thing here. Okay, this is a solvent. This is a semi-permeable membrane. This is a semi-permeable membrane. Assume membrane is present here. Semi-permeable membrane. Okay, so here some solvent molecules are there. Okay, solvent plus solute molecules are there. Solvent plus solute molecules are there. So students, what is this osmotic pressure? So what is this arrangement I did? So first let me explain you one thing. So listen, if we consider a salt water, if you put a grapes or a potato on that salt water, the cells will shrink. The size of a potato or a grapes become what? Less. Okay. If we water into some flowers, okay, some flowers are there. If we kept them in the water, means they become shiny and they become healthy, they feel fresh after some time when we keep them in a water. Okay, and at the same time, our body so our body, what happens, sometimes we absorb the atmospheric air, we feel the breeze, we feel the sunlight, we feel the sun rays, we feel that it is hot. Okay, it is acts as like a membrane. Okay, so from that we will use to see one thing, students. Pig bladder is there. That is also example for a membrane. Exchange of molecules takes place. So one example, as I told you, if the potato is kept in a saline water, salt water, then the size of the potato shrinks. Okay. So what happens here? So listen. So here solvent molecules are there. Here solute plus solvent molecules are there. It is not that I am not telling. It is a solvent only. It is solute only. If solution is there, in that solution we keep. Here it is a solution mixture of solute and solvent particle. If we keep here so many solutes are there. Solvent is this. Here only solute is there as well. Okay. In solution we keep the membrane, semi-permeable membrane. So in between the solution is divided into what? Two types of solutions. Here the solute particle is less, solvent particle is more. Here the solvent and the solute particle is, here solute particle is more compared to the solvent particle. Okay. And R equal, okay, just compared to this, here solute particles is more, solvent particle is less. Here solute particle is less, solvent particles is more. So here what happens? What is osmotic pressure and what is this process is called as? Okay. So first, listen, Here, the concentration is always based on what? The number of solute particles. If the number of solute particles are more, then concentration is more. If the solute particle is less, then the concentration is less. So here, the solute particles is more means this is concentrated solution. Concentrated solution. Okay, so this is dilute solution. Are a low concentration here high concentration. Understood? So here what happens? This is the semi-permeable membrane. It allows only macromolecules to pass through it. Macromolecules to pass through it. Okay. So then what happens if it allows the macromolecules to pass through it, students? Then what happens? Here the solute is there, solvent is there. Always what happens? The concentration of the water is taking place from what? Lower concentration to the higher concentration. So here the water, here solvent concentration is low, here solute particle is more. As I told you, solute particles is a non-volatile or maybe a solid. These are bigger size molecule. Okay, this solvent is a water. Okay, this is smaller molecule. Okay, always the water moves from what? Lower concentration to higher concentration region. Here it is low concentration is there because of the less solute particles are there. Here high concentration is there. So then what happens? This solute, this solvent, the water molecules, the red one, starts move from this position to this position. This is a semi-permeable membrane. It allows these to pass through here. Only this. It stops that black color molecule. So if this is also try to go means it stops here only. Understood? So the semi-permeable membrane never allows the solid particles to pass through it. So it allows only a solvent particle. So that's why this is also called as what? This is a semi-permeable membrane. This is also called as selective membrane. Only selective particles can pass through them. Okay, so then what happens here? It allows this solvent molecules to go here. I hope you understood. The solute or the solvent molecules goes here until the concentration will become both equal, until the concentration attains dynamic equilibrium. Okay, so here solvent molecule is there, here solute particle is also there, here also solute particles are there, the solvent particles move here. So students, here the volume of the solution increases. If the volume of the solution increases, then what happens? Vapor pressure also increases. And you may assume vapor pressure or only pressure increases. Okay, so if this allows the movement of this solvent particle to pass through it, if that increases the concentration of the solvent particle, in this that results in the increase in the volume of the solution. If the volume of the solution increases, pressure increases. So this process is called as what? The movement of solvent from lower concentration to higher concentration is called osmosis. Is called what? Osmosis. The movement of solvent from lower concentration to higher concentration through semi-permeable membrane, that is called as what? Osmosis. Here we are going to check what is osmotic pressure. So here the movement of this will take place, correct? So to suppress the transfer of or a movement of solvent from one concentration to another concentration. For example, here in both the case, the atmospheric pressure is 1 atm initially. So it becomes 1.5 atm after this. This is 1 atm, this is 1.5. Assume, okay? So initially both are 1, 1. After that, this becomes what? And right here, initial pressure. Both the side 1:1. Final pressure. Final means after this 0.5 is to 1.5. Here 0.5 pressure increases. So that 0.5 pressure is called as what? Osmosis. Because of that the pressure increases. So what is osmotic pressure means? The pressure which is applied to stop the osmosis. Okay? The pressure which is applied, because your pressure is more, your pressure is less. So your pressure increases means we have to suppress this. Means we have to apply pressure from this solution. So if pressure applied on this, then again the solvent molecules come back to the original solution. So the pressure applied to stop this osmosis is called as what? Osmotic. So I write here what is osmotic pressure. The pressure applied to stop movement of the solvent through semi-permeable membrane called as osmotic pressure, that is represented by pi. That is represented by what? Pi. Okay, this is called osmotic pressure. So the pressure which is applied to stop the osmosis process, that is called as osmotic pressure. So in this osmotic pressure, as I told you, it is directly depends upon what? The concentration of the solute particle and the solvent particle. Here we are considering solvent students. So before in the depression in freezing point and the elevation in boiling, we consider them with the molarity. But here we are going to consider it with the what? Here we are going to consider it with molarity because we are considering the liquid solution. We consider the transfer of what? That's the solvent, the movement of the solvent from the lower concentration to the higher concentration. That is especially solution. Why solution? Because if the solids are there, this is the semi-permeable membrane is very thin, it has very small pores, so it cannot allow that solid particle to pass through it. If it is in ionic form, very small size, in a solution form, then only it can allow the particles to pass through it. That's why we are considering what here? We come with molarity, not molarity. Okay. So, to consider that osmotic pressure is directly proportional to a molarity and C of the solution is the greater temperature. For example, if you want to derive the equation further, pi is equal to C or D is the equation for the osmotic pressure. So C means what? Concentration. Molarity. What is molarity? Number of moles of solute present in 1 liter of a solution. So here C is equal to what? Number of moles in the volume of the solution. 1 liter of a solution means volume. So this becomes pi is equal to N by V RT. Pi is equal to N by V RT. So what is this N? N means the weight given by molecular mass. Weight of a substance divided by molecular mass. Here solvent is there, solute is taken as 2. Other solvent is taken as 1, solute is taken as 2 means, so pi is equal to W2 RT divided by M2 V. If we want M2, we will get W2 RT divided by pi V. Okay, so this is the equation. By using osmotic pressure, we can calculate the molecular mass of the substance. Here, R is the universal gas constant. You know the value, that is 8.314. Okay, and this volume means, that is volume of the solution. The W2 means the amount of a solute dissolved in this respective solution. And T means the temperature, and temperature should be in what? Kelvin. Okay, and pi is the osmotic pressure. Okay, so this is our what, students? The osmotic pressure and its equation. Okay, so I'll explain one thing. Osmotic, again it is. So the osmotic pressure means, I'll just represent a diagram. This diagram shows what? The transfer of the solvent from the lower concentration to higher concentration. So this complete process is called as osmosis. When the osmosis takes place, the pressure of one side or either side of the semi-permeable membrane, the pressure of these two increases. Okay, here pressure decreases, here pressure increases. Because here only the concentration attains equilibrium, not pressure. Okay, here it is 0.1 concentration means here it also attains 0.1 concentration. Concentration depends on what? Number of solute particles dissolved in 1 liter of the solvent. Okay, so 1 liter of the solution. Here only 2 is there, so we require less amount of, for example, 4 gram in 100 ml and 4 gram in 1000 ml differs, correct? So 4 gram in 100 ml means it is 4 by 100, 0.0. 4 by 100 means that is 4 moles. 4 divided by 1000 means 1 divided by 100 consider. 1 divided by 100 means that is 0, 1. 1 divided by 1000. 1. So 1 divided by 10,000 means 0.1. So then here in both, that's what I am telling here. Here 100 ml is there, here 1000 ml is there. So only one molecules are there on either side as well. So 1 divided by 1000 means 1 mole. 1 divided by 10,000 means 0.1. So the concentration changes. That's why if the solute particle increases up to 10, if the solute particle increases up to here 1 out of 100, here 10 out of 100, then it becomes 1 mole. Okay, that's why if the solute particles is more, then the solvent particle must present. So these two forms what? The uniform concentration. Okay, when they attain the equilibrium at their concentration, then here the volume of the solvent increases, results in the increase in pressure. So to stop the increase in pressure, the pressure applied to stop this osmosis process, that is called as the osmotic pressure, represented by pi. So pi is equal to CRT. Why it is compared to C means because we are comparing here solutions, that's why we are considering what? Molarity. So here pi is equal to CRT is there, pi is equal to N by V RT, pi is equal to W2 RT by M2V, M2 is equal to W2 RT by pi V. Now we are considering concentration means number of moles by volume, number of moles means given weight divided by molecular mass, then we will get this equation. Okay, so I hope you understood, students. So then the next one is how the solutions are classified based on their osmotic pressure. How the solutions are classified their osmotic pressure. Okay, I write the diagrams here. It came to know, students. Isotonic, hypotonic, hypertonic. Here, isotonic is there, hypotonic is there, and hypertonic is there. So if you observe, okay, so I write the diagram here. Diagram is there. Okay, students. So this figures represent what? The isotonic solutions or hypotonic solutions or hypertonic solutions. This is isotonic and hypertonic. Okay. So here two solutions are there. Assume this is one type of a solution inside. This is also one type of a solution. Assume the potato placed in what? A saline water. So then what happens, students, here? If the two different solutions are there with the different concentrations, then this type of reaction occurs. If so, this is called as isotonic solution. Why it is called as isotonic solutions? So listen here. Osmotic pressure of two solutions are equal. Means, students, if we keep here the solution inside this and the solution outside this semi-permeable membrane is equal. So osmotic pressure of two solutions are equal, then it is said to be isotonic solution. So comparing this isotonic, we can classify hypotonic as well as hypertonic solution. So what is hypotonic means? The flow out of the cells and then stream. So listen, here the concentration of this solution is more and this solution is less. Okay, so then what happens? Here the solvent molecules is transferred from here. This is a concentrated solution. This is dilute. Okay, so otherwise what happens? Solvent transfer from what? Dilute solution to concentrated solution. So compared to this, as I told you, if the concentration of this solution increases, then the solvent molecules transfer out of the cell. Okay, then they transfer out of the cell. So this is a semi-permeable membrane. Solvent transfer from this to this. Okay, so then what happens? The shell compared to this it shrinks. So the size decreases. So this type of solutions are called as what? Hypotonic solutions. Here, what happens to the osmosis means So here these are blood cells. Okay, blood cells in this solution. This is 0.9% consists of that much of concentration. Here we consider NaCl means it is highly concentrated. If the solution inside the cell and outside this water or the solution is equal, then it is isotonic. If the pressure inside or the osmotic pressure of solution is greater or pressure in blood cell is less than solution. Then what happens? This solid molecules inside the cell is transferred to what? The solution. Then the cell shrinks. At the same time, here the concentration of the solution is less. Here the concentration of the solution is year more, year less. Okay, so then what happens? Now here the high concentration is there, here least concentration is there. Then the transfer of solids or movement of solution or the solvent, this takes place from low concentration to high concentration. Here I write this is concentrated here, this is dilute here. So this is dilute means the solvent move inside the cells. So then what happens? The size of this blood cells increases. So here the osmotic pressure inside the cell is more compared to this solution. Okay, the osmotic pressure inside the cell is more compared to solution. Okay, so students, I told you if osmotic pressure of two solutions are equal, then they are called as what? Isotonic solution. If the osmotic pressure of the blood cell, I am taking here, blood cell is less than solution, so then it is what? Hypotonic. If the osmotic pressure inside the cell is more, then it is hypertonic. So comparing this, if the shell shrinks, then it is hypotonic solution. If cell size increases, then it is hypertonic solution. So this is about the types of the solutions. Okay. So another one thing is that is reverse osmosis. Another one is reverse osmosis. What is reverse osmosis, students? I think you are all known about. Sometimes if you observe the advertisements of any purification water purifier, they said they are RO purifiers. Okay, they said RO purifiers. What is that RO purifier? So the osmosis, sorry, the process that RO purifier means reverse osmosis. The water can be purified by the process reverse osmosis. Okay. So when it happens, when the pressure is more than the osmotic pressure, then what happens? The solvent can transfer from one position to another. For example, I will say, so reverse osmosis means, this is the diagram. So this is the semi-permeable membrane. Assume, okay. Here pure solvent is there. Here this is water, pure water. This is saline water. Saline water means solute particles are there along with the water solvent. Here only solvent particles are there, pure. So then what happens? Here concentration is more, here concentration is high means the process can take place, the solvent molecules can move from this to this. Assume this one is A, this one is B. If the the movement of the solvent takes place from A to B, that is osmosis. Then what happens? Pressure exerted here. So instead of that, what is this reverse osmosis? Reverse osmosis. What is this reverse osmosis? We are applying more pressure here. So instead of to stop the movement of the solvent particles from this A to B, so we apply more pressure here. If we apply more pressure, what happens? The process takes place in this manner. That is, the solvent particles try to move from B to A. So this is called as reverse osmosis. So when this happens, so listen, if the pressure applied is greater than the osmotic pressure, then the reverse osmosis takes place. For example, here 1 bar pressure is there, the osmotic pressure is 2 bar. Okay. If we apply only 1 bar pressure, then osmotic pressure over will the normal pressure. So then what happens? The osmotic pressure prefers. So solvent can pass through from A to B. Then we apply 3 bar pressure to this side. Then what happens? So osmotic pressure is 2 bar pressure, the applied pressure is 3 bar. So then it is greater than the osmotic pressure, it can have the ability to reverse the reaction. So that is reverse osmosis. As I told you, here already a pure solvent is there. So here solute and solvent is there. If we apply the extra pressure to this, only solvent particles move from the semi-permeable membrane. So only pure water move from here to here. So RO purifier means reverse osmosis purifier. How this reverse osmosis takes place? By applying the extra pressure which is greater than the osmotic pressure. So I write here, if the pressure applied greater than osmotic pressure, then it is called other than reverse osmosis. Then reverse osmosis takes place. I hope you understood. But if the pressure applied greater than the osmotic pressure, then the reverse osmosis takes place. This is the diagram which shows the reverse osmosis. Okay. So here what happens? Always the pressure is greater than osmotic pressure. Pressure is greater than osmotic pressure. So this is all about the reverse osmosis. So another point is that is normal and abnormal. Then right here, abnormal mass. Abnormal mass. So what is this abnormal mass? For example, consider KCl and CH3COOH. KCl in water, CH3OH in benzene. Here this is solute, this is solvent. This is solute, this is solvent. So why I have taken this? I told you polar molecules dissolved in polar solvent, non-polar molecules dissolved in non-polar solvent. So here, when this KCl and H2O is taken, it is easily dissociates into K plus and Cl minus. We will get the normal mass after equal masses before and after dissociation or association. Okay, so this is one thing. If you consider CH3COOH in presence of C6H6, How this will return? CH3, C double bond O, OH. CH3, C double bond O, OH. Here also CH, C, CH3, OH, double bond. Both are this one, CH3COOH and CH3COOH are I arranged in this manner. So students, in the benzene ring, if in the presence of the benzene as a solvent, if the dissociation of this takes place, what happens? They form a hydrogen bond here and they form dimer structure. Due to the formation of the hydrogen bond, instead of dissociation, they form what? Dimers. So dimers of acetic acid takes place. So then what happens? If the dissociation takes place, we will write in this manner, that is CH3, COO minus plus H plus. Only few molecules are dissociates and few forms what? Dimers. So then what happens? The mass of the ions formed is less compared to the mass of the solid particle. So this is the normal mass. For example, CH3COOH. This is 100 mole is there. Here only 50 moles are dissociated. So then what happens? Here 100 mole is there, only we got 50 moles are dissociated, means there is a change in what? 50, there is decrease in the mass. So the mass of 100 mole of the substance and the 50 mole of the substance is different. Correct? So here what happens? This shows the decrease in the masses of after dissociation or association. So decrease in the masses of these ions before and after dissociation. So to attain the abnormal mass of this, so then what happens? The scientist show a factor I, that is called as Van der factor. So what is this Van der factor gives? It gives the ratio of normal mass to the abnormal mass. What is the abnormal mass? Is either increase or decrease in the masses of the substance after dissociation or association compared to normal mass. Okay, what is abnormal mass? Abnormal mass means the increase or decrease in masses of solute, the masses after dissociation or association the ratio of increase or decrease in masses after dissociation or association with to the normal mass called as what? Abnormal mass. Either increases or decreases. So here it increases. The ions are equal or maybe increases. Here it is decreases due to the formation of what? The dimer. So due to the increase or decrease in the masses of the substances is called as what? So the masses of the solute particles after dissociation or association is called as the Van der factor. So that Van der factor is why it is called like so means because it is determined by the scientist Van der. Okay. So what is the equation of the Van der factor? Means I is equal to normal mass by abnormal mass. Normal mass by abnormal mass. Or you may also say this is I is equal to the calculated colligative property divided by observed colligative property by calculated colligative property. Normal mass by abnormal mass or observed colligative property by calculated colligative property. Also, you can also say total number of moles of particles in association or dissociation divided by number of particles after association or dissociation. Okay, so you can also write total number of particles by number of particles after dissociation or association. So this is all about what? Quantum factor. Important for one mark. What is our quantum factor? Okay. So this gives the observable mass. What is observable mass? The ratio of increase or decrease in the masses of the substances after dissociation or association with respect to normal mass is called as abnormal mass. That is explained by the quantum factor. I is the normal mass by abnormal mass and observed calculated property by observed colligative property by calculated colligative property. Okay, so once we have the abnormal mass, then how this colligative properties changes? As I told you, this is the colligative property. Once we got that, how the colligative property formulas changes. How many properties are there? 4 are there, right? We derived the respective formulas, so we can easily write relative lowering of vapor pressure. So here P1 naught minus P1 divided by P1 naught is equal to N2 by F1. Correct? So you may take it as N2 by N1 is enough. So this is multiplied by height. Okay, so how the formulas changes if we apply quantum factor. Next, elevation in boiling point. What happens? Delta B, delta TB is equal to KB into W2 into M1 divided by W1 into M2. So this is also multiplied by I. So next, depression in freezing point. So delta TF is equal to KF. So I into KF W2 into 1000 divided by W1 M2. Okay, next, osmotic pressure, that is equal to, osmotic pressure is represented by what? Pi. Is taken as what? High CRT. And we will take it as high W2 RT divided by F2. So this is the formulas we are going to consider after we apply abnormal masses. Okay, so this completes the theory part of the solution. Tomorrow we will discuss a very important topic, that is one topic, the very important part of this, that is problems based on this colligative property.